Hello, and welcome to another edition of The Tutor Wizard. I'm your host, Willow's dad. Actually, I'm Willow's uncle, but I'm working on being Willow's dad. My name is Tim, by the way. I am not a cat, but if I was a cat, I would look like that, because that's just sexy as all hell. A rag doll laying in a field of clover. Does it get any better than that? Probably not. Anyway, we have the Introduction to Statistics lecture number 9 tonight. Continuing on with probability, we're going to look at tree diagrams and several random variable examples. We'll probably still have one more to go after this to do a reasonable coverage of the entire topic of probability. But tonight we have 6 of them lined up. Actually, a bit more than that. There's subtle questions. And we should probably dive right in. Let's get started. All right, let's have a look at this one. I did a little preparatory work on this. You can already see the trees already set up, but we need a question here. So whenever you see a written question like this, it talks about false positives and false negatives, you probably want to do a tree diagram. It's not the only way, mind you. It's the way I prefer to do it. Seems to be a easy to understand method as opposed to getting into a whole bunch of just terse probability notation, which for most students makes their brains just go. Well, it makes my brain go. So I expect your brain will go too, because I'm not a rocket scientist. So here we have a condition. I'm going to leave it open. You can decide whatever it is. A condition is present in 10% of a given population at any time. The test that detects the condition is correct 99% of the time and 95% of the time for positive and negative conditions, respectively. So what does that mean? Well, the 99% then is a true positive. Let's make a note about that. So true positive, I'll just do it this way. T with a positive sign, that's equal to 0.99. And the 95% refers to a true negative. Okay. So that's the first thing we have to do, is come to an understanding of the information given. Now, I don't usually go out of my way to make questions deliberately hard to follow, because I want you to learn how to do this stuff. I'm not interested in torturing you with your reading comprehension, but that doesn't necessarily mean others won't. So there's 2 questions here. First question is, what is the chance of a positive result? And the second question is, what's the chance the test is correct given that you already have a positive result? Because remember, there's 2 ways to get a positive result. There's a true positive and a false positive. And there's also a false negative. We should probably write that out. Let's do that. So if I know that the true positive rate is 0.99, then if the test is wrong and the person has the condition, then we have a false negative. All right, so the false negative then should be 1%. And likewise, we should have a false positive, which is the case when the person is healthy, but the test erroneously says they're ill. And that'll be 5%, because this stuff always has to add up to 1. You'll notice that 99 and 1 is 100%, and 95 and 5 is 100%. All right, let's move on to this little diagram thing here. Now that we have an understanding of the numbers, this is our starting position. So let's say when a person comes in off the street, this branch of outcomes, this will be the positive side, and this branch will be the negative side. Now, we know that in the population, 10% of the people have this condition at any time. So we're going to write 0.10 here, and since 90% don't have it, we'll put 90 over here. So at this stage, you can see that this adds up to 100%. Now we come to these two forks, here and here. We'll do the upper branch first. This is the positive branch. So we have to label this. So we can have a true positive, which I'm going to put arbitrarily on this branch, but we can also have a false negative. That goes there, because remember, the person who come to our clinic has the condition. The test is wrong, so it's still in the positive branch. Now, I'm told over here that a true positive rate is 0.99. Let's write that down. And the false negative rate is at 1%. Boom. There we go. Now let's go to the other branch. We can have a true negative, because remember the person is healthy and the test is correct 95% of the time. However, we can also have things go wrong and get a false positive, and that happens 5% of the time. Boom, there we go. So, with this laid out, now, let's see, we have an ad. Okay, but now we can find the 4 possible outcomes. We're going to let this scroll on, and then I'll figure this out. All right. Okay, we'll let these ads run, and then we'll fill in these boxes. Got some different ads tonight, too, I see. Cool. Come on. Okay, we're back. All right. So we have to figure out what goes into each of these boxes because there are 4 separate outcomes here. Now let's look along the top. I've got a person who has the condition and the test says positive. You have the condition. How do you get that? You get it by multiplying along the branch. So this result here is going to be 0.10 times 0.99. Now I've already pre-worked this stuff. That doesn't mean I can't screw it up. Did I write something down wrong here? True. Positive. Oh, I put the wrong numbers in on my notebook. So you know what? We'll just redo the calculations right from scratch because I have them backwards on my notebook. That's bad. Okay, no biggie. Let's carry on. Wayward son, there'll be peace when you are done. You lay your weary mind to name the band. Yes, you would have saw that song sung by Dean on Supernatural, but it also came out in the late 70s too by another band. Okay, let's multiply this up. Well, the 10% of 99% is easy enough. That's just 0.099, but we're going to do this anyway because I've already turned my calculator on. All right, so this is 0.099. And we're going to go to 4 decimal places. Now let's multiply along the next branch. So again, we have a true positive, or pardon me, we have an ill client, 10%, and then we have to have 1% of that, and that should work out to 0.001. And we'll put that in here. I chose these numbers to be reasonably easy to work with. The idea being on an exam, if you forget your calculator, you should expect that the numbers shouldn't be terribly hard to work with. No guarantees about that, because remember, I'm not making your exam, but if it was me, I would make things relatively straightforward for pencil work. Now, let's go down to the healthy branch, the negatives. So here we have 90% of the population are healthy. And the test is correct and gives us a true negative of 0.95. So this is going to be 0.95 times 0.90. That'll give us this result. And what do we get? 855. There we go. And lastly, we'll multiply along the bottom branch where we want 5% of 90. And we're going to go 0.5 times 0.9, and that should be 0.0450. Now, the way to check this doesn't guarantee you got it right. I mean, multiple mistakes can happen, but everything here should add up to 100%. So let's check that. So we got 0.855 plus 0.045 plus 0.001 and 0.0990, and I get exactly 1, so we know we're reasonably correct. Sums to 1. Correct. Okay. So this is all the work we have to do to prepare to answer the question. Hey, Logarithmic, welcome, welcome. Yes, I try to keep my numbers relatively easy for people to work with just by bouncing that decimal back and forth, and sometimes dividing by 2, because like that last computation, we know 10% of 0.9 would be 0.09, but I want 5%, so I divide by 2, and that gives me 4.5. So yeah, that's the sensible way to do it. However, it's been my observation, and maybe yours too, that people do have a dependency on their calculators. So anyway, moving on. Okay, so what's the chance of a positive result? So we want question 1. The chance of a positive result is the sum of the true positive and the false positive. So the true positive, that was this one right there. There's your true positive. We have 0.099, and the false positive was 0.0450. So this should work out to 0.1350. Bazinga! So that means just under 1 chance in 7 of getting a positive result, but that doesn't mean you're guaranteed to have it because there's a built-in error rate here. But we can compute that. Number 2, what is the chance the test is correct given that it's a positive result? So we're going to set this up. This is essentially a conditional probability, which we talked about in the previous lecture. But what it comes down to essentially is this: the probability of a true positive divided by the sum of the true positive and the false positive. Now we already know the denominator is 1350. And the true positive was 0.099. Okay, I kind of messed that up. Let's try that again. So if we divide this out, we'll have our answer. And like I said, I had done this earlier, but I made a boo-boo, so we're just going to do it right over again. 0.099 divided by 0.135. Did I key that right? Looks like it. Yes, I did. 73%. 0.7333. There we go. So this is oftentimes why, if this was a serious medical condition, probably would repeat this, because there's a significant error rate here. The false positive error rate, this one here, is pretty high. So if this was a life-threatening illness, they'd probably redo the test. But this is just a silly little example, and we're not going to worry about it. So there's how to do a tree diagram. Again, the idea is if they start talking about false positives and false negatives, true positives, true negatives, this is probably the way you want to go. You may see it illustrated as an example in class with just terse probability notation, but yeah, I like to draw pictures, so I'm not going to do it that way. Now, let's move on to the next slide. Okay, so we're working with some discrete probability questions tonight as well. And here's the layout for a game of chance. So let's say, for instance, that we have an urn. Can I draw an urn tonight? I'm not really the most artistic fellow for these things, but okay, it's more like a bag. Okay, it's a bag, okay? It's our bag. And in this bag is a collection of red, white, black, and blue marbles. And if you reach into the bag and pull out a red marble, you win $20. You have a 10% chance of that happening. If you pull out a blue marble, you win $10, and you have a 20% chance of that. Black has a 30% probability, and you win $5, and there's a 40% chance that you grab a white marble in which you lose your stake. You win nothing. We're going to figure out two quantities, and then we're going to ask a conceptual question. So let's look at number 3 first here. That's this one here. If I say the stake to play, so that's, you got to lay down some money to play the game. If I say the stake is $5, we want to know who has the advantage. So it's either going to be the game runner, or it'll be the sucker, the player, the patsy, the townie versus the carny. Now, the way you answer that question is hiding in number 1. If the expected payout is greater than the stake, then the advantage lies with the player. If the expected payout is less, then in the long run, the advantage lies with the game runner. Remember, when we talk about advantages like this is long term. Anything can happen on 1 or 2 plays of a game, but if you play this game 100 times, that's different. And the true behavior of the game should come out. For instance, if you play this game 100 times, then you have put down $500. I'll make a note of that so don't forget. 100 plays implies that you have laid out $5 at a time, $500. We're going to come back and see whether we win money or we expect to be ahead of the game or behind the game after we find the answer to question number 1. Question number 2 is what's the standard deviation? In other words, how consistent numbers are. So there's formulas for this stuff. They're usually on your formula sheets. The expected payout, or the expected value, remember, this is just another way of saying what's the average value. So I'm going to use the dollar sign. The expected winnings. This is going to be the sum of each outcome. So when we talk about outcomes, we're talking about the payout here. So this is going to be some number of money times the probability of winning that money. So for red marbles then, that's a $20 win. And we're going to multiply that by the probability, which is 10%. So in other words, this cell times this cell gives you a value. And that value is $2. Now, let's go on to the next one. Now we have a $10 payout, and this happens 20% of the time. So this one, coincidentally, is also $2. If you pull out a black marble, you'll win a $5 bill. In other words, you get your stake back, break even. That's 0.3. This is $1.50. And finally, losing your money happens 40% of the time, and you get 0. So if we add this up, because remember, this is a summation operation, this adds up to $5.50. Well, that means the advantage lies with the player. 100 pounds on 0 factorial. But you know, 0 factorial, Sensation Black, that's equal to 1, right? Because we're doing math here, so that exclamation mark means factorial, right? So that means you're a winner. Anyway, so here's the answer to this question. We know that the stake is $5, but each play has an expected return of $5.50. So over the course of 100 plays, on an average of 0.55, then that's a $550 return. So you're $50 ahead. There we go. Easy enough. Now, so Sensation Black, you're in the United Kingdom, or Britain, I suppose. Well, let's see now. United Kingdom, so Scotland, Wales, England, Northern Ireland. I think I got that right. Because you're using the pound symbol. Never been to Britain. It would be kind of interesting, I think. Now, what am I doing here? We want standard deviation. Now, we need some more room for that. I'm not going to make it fit here. I'll write the formula down, but then we're going to have to go to slide this down. I'll move it. You know what I'm going to do? I'm going to make a new slide. So insert a page. So now we want the standard deviation of the expected winnings. So this formula is a bit more complicated. This is going to be the sum of each outcome. So I'm just going to use my own notation here. So that's dollars minus the expected outcome. I'm going to use E of X here, but oftentimes they use the Greek letter mu, they being the people who write textbooks. Of course, this has to be squared, and then we're going to multiply it by the probability of that outcome. So this one's a bit more complex. So let's do that. So the first winning was $20, and we're going to subtract $5.50, or £5.50, or €5, 5.5 euro. Okay, and this was times 10%. That'll give us a value. I'll grab my calculator here in a moment. I have this worked out too. I can just read it off my notebook. And then the second one was a $10 payout, but again, we still have the subtract the expected, square that. This is times 0.20. Moving on to number 3. This is where you break even. Well, theoretically. This is times 0.3. And then this is where we can't ignore the 0. You'll notice that with the expected value, the 0 is just basically a throwaway, right? But here it's not, because we're going to end up having to deal with this. And we'll square that, and this is times 0.40. So there's 4 computations there. And let me just grab my notebook. Now, how did this work out to? Oh, I didn't actually do the intermediates. How silly. Apparently I'm a bit of an idiot. Well, that's not a surprise to anybody who knows me. So, I kid, I hope. Here we have 1450 squared. I'm just going to write this out because, you know, sometimes it's not okay to skip steps, especially when people are learning this stuff. So I have to remind myself of that on occasion, that what might seem simple to me isn't necessarily simple to anybody else, because I do this stuff all the time. So here we have negative, did I screw that one up? No, we got 50 cents. I oftentimes find I go back, look at my notebook, and I'm going, why the hell did I write that? The hell was I thinking? Or this quote, I think it was Dave Chappelle, cracks a hell of a drug. I kid. I kid. And here we have negative 550 squared times 0.40. Now, these are all going to work out to values, which I am going to compute. I already know what the final answer is, but for those of you who are working along or want to work on this later, let's do it properly. So here we have 14.5 squared times 0.1. That's 21 and 0.25. Then we go to the next one, which is 4.5 squared times 0.2. We got 405. There we go. Then we have negative 50 cents. Negative 50 cent. Boy, he's really, 50 Cent, by the way, is really roasting Diddy. And if you've been following that, not usually a big follower of pop gossip and such, but P. Diddy is on trial, and 50 Cent, who has no love for P. Diddy, has been roasting him good. Man has got an acid tongue. Yeah, we got 5.5 squared times 0.4 and 1201. 12.100. Okay, now let's add this up, because remember, this is a summation operation. Remember, this thing right here means to sum your results. Got to throw a root on at the end. You are right, because this right now is variance. Let's add that up. 12.1 plus 0.75 plus 4.05 and 21.025 gives us 37 and 25. So the variance of the payout is 37.25. Now, standard deviation of our payout is going to be the square root of the variance. And that works out to, let's just do it on the calculator. That works out to $6.10. I'm just going to use the 2 decimals because we're talking about money here. There we go. That's how you do that. So these, in my experience with the university I work at, these are pretty common questions for midterms. Might even be on the final too, simply because of the complexity of the calculation. And, well, you know, it's a cumulative final almost always as well. So you'd be wise to get comfortable with doing this computation. I had to stop for had a bit of a drink there. It's quite dry in here tonight. You know, we've had 3 days of rain. It's still a little, in my home, it's still a bit dry. Hey, let's move on. Let's move on to the topic of linear combinations for random variables. So this crops up when they give you, well, in the case of singletons, that's these two here, where you have to modify some parameters. But if you want to modify and or combine 2 or more random variables, you use these two. We're going to do examples of both. So the first one, we're going to let the mean of the random variable x be 10, and the standard deviation will be the value 5. And we're going to apply a transformation to both parameters. Transformation will be 6 times the random variable minus 20. So what do we have here? The mean, remember, for random variables is capital E of capital X. Standard deviation would be SD of X. Now, if you look closely up here, we talk about variances. If you're going to use these formulas, you have to convert the standard deviation to variance. If you're going to screw this stuff up, This is where you screw it up at. So let's square this. So this becomes the variance of x, and that's simply 5 squared, or 25. So if you don't forget to do that, you'll probably get this correct. Okay, well, let's modify the expected value first. So that means we're going to use this formula right there, that number 1. So let's write it like this. Here we have e, and I'm using 6 times this minus 20. Now, here it doesn't matter to do this, but it is important for one of the ones coming up here in a minute. Subtraction is really the addition of a negative number. And this is going to bite you in the ass if you're not careful. You'll see that in a moment. All right, so we've matched this formula. Now we have to turn it into this and simplify. So this is the value of A, this is given, and this is the value of B. So this is going to be 6. Now the expected value of x is 10. And then we're going to add negative 20. Well, remember, that's just subtraction. You know that. So this is going to be 60 minus 20, and we get 40. That's not rocket science. Now, let's take a look at the variance. Oh, and by the way, you'll notice here with the variance formula inside v of ax plus b, we're adding a constant. But it's not here at the end. Because with variance, we don't add or subtract constants. That's not a mistake. It's blank because we don't do it. It means don't do it. All right, moving on. Variance, 6 times x plus negative 20. Well, what is that going to turn into? Well, that means we need, remember, this is a, so we got to have a squared times the variance of x. So a squared, that's 6 squared, and the variance was 25. So this is 36 times 25, and unless I miss my guess, that is 900. That's the variance. But what's the standard deviation? So standard deviation then will be the square root of variance, and we should get 30. There we go. So those two are pretty straightforward. Actually, the next two are pretty straightforward as well. There's just more of it. Sometimes complexity isn't harder, it's just more. And that's what we're going to have here for numbers 3 and 4. There's just extra parts. And again, the same thing. Now we're going to use the same numbers for x. But now I have the mean of y. So this is going to be e of y is 20. Standard deviation of y is 2. So that means the variance of y is 4. And we have room here to do that, so let's do that. We're going to look at equation 3 to do the expected value. We're going to have e of, so remember, we are using this transformation now. We're going to have 6x minus 4y. So now we're going to go plus negative 4y plus 20. So that's this piece. Now we're going to rewrite it as this piece. So we have 6, and the expected value of x, as we know from earlier, is 10. Then we're going to add negative 4, and the expected value for y was 20. And then we're going to add 20. What do we get? Well, this is 60 minus 80 plus 20, and this works out to 0. There's nothing significant about that. When I made this up, it just worked out that way. And I thought, well, that's kind of cool. We'll just leave it alone. Now, let's take a look at the variance. So now we're going to have v. Again, we're going to have 6x, negative 4, y, plus 20, just like before. But now we're going to have 6 squared, and the standard deviation for x was 25. And here's where the gotcha comes, okay? If I had written this simply as minus 4y, and I wasn't paying attention to business, I would write minus 4 squared y, and I would be wrong. We need to square away the negative on the negative 4. So we have adds going. I'm just going to finish writing this out, and then we'll get down to business. Okay. We got one add left. We're almost ready. And we're coming back. And 2, 1, and we're live. There we go. All right. So just to recap, because there's some ads running here in the stream. If I had written this simply as minus 4 times the variance of y, and I wasn't paying attention to what I was doing, I would be simply squaring the 4, and I'd end up with 36 times 25 minus 16 times 4, and you would be wrong. We always square away negatives, so it's kind of important to pay attention to this, because variance can't have a negative number anywhere in there. Because remember, to get standard deviation, we have to have a square root. Did I screw up? Oh, nope. Oh, thanks, logarithmic. I see what's going on there. Yep. Okay, so anyway, to make a long story short, variance can never be negative. Especially if you look at the formula for the broader formula, it's going to be the sum of squared values. There's just no way to be negative. You can't have it. So if you end up subtracting something in a formula like this, you've done something wrong. So this is the variance, but we want the standard deviation, and that will be the square root of 9. I said 9, not 694. I want 964. So this is going to work out to about 31 and a little bit. I did work that out. Where is it? 31048. There we go. So that's the modified or transformed standard deviation. So this is a rather mathematical topic, so that means it's a good question for exams. Zone Ranger, don't you need conditions on X and Y so that you can calculate da-da-da-da? Not sure if you mentioned them. Basically, the conditions that I'm concerned with are positive values or not just positive values for variance. Because remember, if A and B are going to be negative values, make sure you write it as such so you square it. You can't have that. And again, we're not going to be adding any constants at all. So actually, Zone Ranger, if you want to throw in on what you were chatting, what conditions you were thinking about, go ahead and do that. And we'll talk about that for everybody else. This is a comment on the chat. I'm basically keeping this pretty straightforward. We're not getting too mathematical with this tonight as far as these linear combinations go. We certainly aren't going to take it over into vector space, that's for sure. I hope not, anyway. Don't x and y have to at least be uncorrelated? Yeah, well, you'd want that, right? So, one of the things when talking about random variables kind of goes without saying is these things are relatively independent. And we generally want them or minimal correlation. If we get them too similar to each other, then this kind of gets silly. Zone Ranger question for you. If you're talking about x and y being uncorrelated or minimally correlated, I guess, trying to think of the discipline. There's an interesting technique when we start talking about vectors and things and correlation of vectors. Principal component analysis, which is really kind of a neat thing, mathematically a bit heavy, do by hand. Software, of course, makes it easy. Have you had any exposure to PCA? And from extension of that would be principal component regression, which makes use of principal component analysis. Kind of cool. It leads to an interesting conversation, and I'm not going to take a huge side trip here because I know I'm going to, the folks that I'm targeting with this discussion, I don't want to scare them off. But if we have a vector, let's call this vector x, and we'll call this one vector y, and the correlation for the centered data would be cosine of the angle between those rascals. That's kind of an interesting computation, actually, doing simple linear regression with linear algebra. I've got a nice example of that written up. The other, with some of the, you know about PCA, good. The covariance of x and y is 0. We would kind of hope that, but we don't get into it too deeply in this particular course. I'm gonna double check on that. I know in this course we never worry about the covariance between the two things. Of course, we don't want to be we don't want to overdo it here either. But what am I trying? Oh, I know what I wanted to mention. So there's two other people on this stream too. There's Adrian, who's the Energizer Rabbit of mathematics, and then Lorenzo. And I know Lorenzo was working on some linear algebra commentary, some lectures on that, and I'm trying really hard to get him to do or once he gets his crew through to a relative point where they know how to do dot products and compute cosine, to do the simple linear regression, or ordinary least squares if you want to call it that, using vectors, which would be kind of cool. That is needed so the variance of the sum is the sum of the variances. Yes, because then it would be linear. And you may be wondering what the heck we're talking about here. So just for other folks, before we move on to the next topic here, if we're talking about linearity of these things, we're going to use the old T business here. So if we're applying a transformation to two variables, here would they be random variables, there's two conditions. So here we have the transformation of the sums, and then if it's linear, we can have the sum of the transformations. So this is what Zone Ranger is talking about when he's talking about, notice the variance of the sum is the sum of the variances. So t of x plus t of y is equal to the transformation t of x plus y. And there's a second criteria for that. We could have t of a, I'll just, if we do it this way, sure, plus ay is equal to, I can take the constant value here out, and whoops, and now we're linear. Now if you're saying, well, this is way too much math for me, think about this for a minute though in terms, if you go shopping, and you have a sales tax. So in many places, it's called a VAT, value added tax. Here in Canada, we call it the GST, or the provincial sales tax, but around the world, it's usually called the VAT, value added tax. So if you buy a number of things, let's say you buy object 1 plus object 2 plus object 3, well, then you can apply the VAT, the value added tax, after you add up all the numbers, or after you add up all the prices. Or if you're doing it one at a time, you can apply the VAT to the first object, and you can apply your tax to the second object, and you can apply your tax to the third object. So it's linear, the application of homogeneity. There we go. So this is the thing about mathematics. Lots of words basically talking about the same thing. So for anybody who's looking at this and saying, this is beyond me, don't think about it that way. You do this all the time when you go shopping. If you keep a running total when you're shopping, you can figure out the final price for each object when you buy it and put it in your cart. Or you can just figure out the total price of all the things you bought and then apply the tax to it. You'll get the same result each time because it's linear. That's the idea. Right. So what we're doing, Zone Ranger, then, just back up a slide here, just again working on the chat. We are making the assumption in this formula here that the covariance of x and y is 0. We're operating under that assumption. We don't want to scare off young statisticians anywhere. Anyway, that's one busy slide. I think that's enough of that slide. Let's move on to the next one. Okay, let's look at some coins and marbles questions. What do we got going on here? So here we have a container that has 30 marbles in it. N is 30. 4 are red, 6 are blue, there are 20 white ones. And we're going to do some sampling without replacement in this problem. First problem we're going to do is, what's the probability of getting 2 red marbles on the first 2 picks? The second question is, what's the probability of getting red or blue on the first 2 picks? And then we're going to look at, what is the probability of at least 1 red or 1 blue on the first 2 picks? This one in particular is a great place to remind everyone that if you're not sure what's going on, try to identify the sample space and then figure out the question from there. I mean, when it's reasonable. If there was, we could make the sample space ridiculously large here, but that's not what's going to happen in this course. So we'll find the sample space of this here in a bit. Anyway, let's look at number 1 first. Probability of 2 red marbles on the first 2 picks. So that's saying, if we write this out, we're asking what's the probability of red and red. And for independent events is a multiplication operation. So let's set this up this way. For question 1 then, we have outcome in this box, and then we're going to have the second outcome in this box. And these are fractions. Now remember, there are 30 outcomes on the first pick, but we don't put, whatever we get, we don't put back in, so then for the second choice, there's only 29. Now we're interested in red marbles. So on the first pick, there are 4 reds in there. Now assuming we pull a red one out, then on the next pick, there's only 3. So this is just fraction multiplication, which is multiply the top and multiply the bottom. So this should be 12, and this should be 870 Why 870? Well, I used a calculator. But the other way is, I know if I take 30, and remember multiplying is just adding repeatedly. If I go 30 and add it 30 times, I get 900. But I'm only adding it 29 times, so I got to go backwards another unit of 30, so that's 870. Now do that with your slide rule, and then you'll really be old school. So what does this work out to? This works out to, I'm not going to simplify that fraction, by the way. So this will be a fairly small number. 12 divided by 870, and we get 0.01379. So about 1 1/3% of the time, that's what's going to happen. Did I get that right? 12 over 870? Yeah, that's right. Okay. Now, that one's done. Let's look at number 2. What's the probability of getting a red or a blue? Now look at the word or here. Or indicates that we have to add outcomes. So we've already figured out red. We don't have to do that again because we know what that is. It's right there. But now we have to figure out blue. Now those are two distinct outcomes and we have to add them together. So again, we're dealing with independent events, so or means add. So we already know we have 12 over 870 right there. Or means add, and now we have to figure out blue, which we'll do exactly the way we did previously, except the numerators are going to change. So this will be 30, this will be 29, this is a 6, and this is a 5. So now we have 12 over 870, and then we have 30 over 870. We have common denominators, so don't let that panic you. That's just 870. And 12 and 30 is 42. So 42 divided by 870 should be our answer. It should be roughly, I don't know, what, 3.5 times bigger, I guess. Let's see what we got. 42 divided by 870, and we get 0.048. Well, that'll round to 28. There we go. So there's question 2. 42, the answer to the question that is the meaning of life and the universe and things. Again, I didn't plan that to work out, but it worked out that way. I almost think there's some special place in the universe for the number 42, if you know what I mean. All right, number 3. What's the probability of at least one red or one blue on the first of our 2 picks? So now I have to have sample space. Now let's do this the longish way. It's not a hard way, it's just the longish way. How many ways can we get values here? Now I'm looking at, let's make a simplification here, at least one red or one blue. So that means we can say RB as a single unit, because it doesn't matter. It could be one red, one blue, it could be 2 reds, 2, whatever. We just want those things together, right? Because we're going to go and do this the easy way. So we're looking at the probability of at least one red or one blue. So we could say, let's rewrite it down here. So I'm going to answer this question in context of the question, what is the probability of at least one non-white marble? That is really another way to reword the question, and that should make this a little bit easier for us. Not enough room to work, I guess. Okay, now we're doing 2 pit. Well, let's do so we can have a white marble and a white marble. There's one outcome. We can have a white marble on the first and a RB on the second. Or I can have my RB on the first and then a white marble on the second. Or I could have an RB and an RB. This is really the only 4 ways this is going to happen. So the easiest way to answer this question is to do this. What is 100% minus the probability of those two non-colored marbles. That's what we're going to do. So what's the probability of a white marble backed up with another white marble? It'll be 1 minus, let's make a box. So there are 20 out of 30 on the first pick, and there are 19 out of 29 on the second pick. So we get 1 minus, now 20 times 19, that should be, why is that hard to do? That should be, what, 380? Sure, that's 380. And this is 870, because we already know that. So this will be 1 minus, where's my calculator? We're going to make sure we have this. 380 divided by 870 is 4368, rounded. So the answer to the question then will be, I'm not going to do it in my head, I'll screw that up for one reason or another, 5632, boing, there we go. So there's nothing wrong with, thinking about how a question's worded and maybe putting it in a manner that is a bit more easier to understand. We could have figured out this probability, and this probability, and this probability, and then added them up, and we would have got the same answer. Now, for instance, if you do it that way, these two are going to be the same thing. So we can just go 2 times whatever that is, and then add this. And I did do it that way as well, but I want to try to keep close to about an hour tonight for time. Just if you're going to work it out, these ones are each 2299. And this one is 2299. And that last one is 1034. So if you do it that way, you got, well, this is 43, this is, 23, 46, 56. Yeah, it works out the same, doesn't it? So you can do it either way. You have choices. Mathematics isn't always about one correct method. Don't let anybody tell you otherwise. All right. Okay, let's wrap up with this question tonight. We have the following independent events. We have physics. Okay, so this is school. We have any random student. A 10% chance of taking a physics course. 15% chance of biology, 20% chance of chemistry. And we've got 4 questions we're going to try to answer here. First one is, what's the probability a student is in both physics and chemistry? Well, and that's a multiplication because these are independent events, right? The probability a student is in both physics and chemistry. Now, I worked this one out. Where did I write the answer to that? Oh, there it is. Okay, so physics, the probability of physics is 10%. Probability of chemistry is 20%. This should work out to 0.02 because numbers are easy to do. Let's look at the second one. What is the probability the student is not in physics but is in biology? So this is kind of a given that. It's kind of a conditional. But remember, these are independent, so we can do this a little easier. What is the complement to physics? So the probability that someone is not in physics, I'll put a C for complement, must be 0.9. Okay, so if you're not in physics, it's 0.9, but you are in biology, which is 0.15. So this should be 135. Okay. What's the probability that a student is in biology or chemistry? So or, that's an addition. But remember, you have the possibility of a double count. If we were to set this up with a contingency table, you would see that. But we're going to do it without it tonight. So for number 3, of the probability of biology plus the probability of chemistry. Now, there's also the possibility that certain students are in both, so that's where we're going to get our double count from. So we subtract the intersection of those, so this is an and. We do that. What do we got? So bio was 15%. Chemistry was 0.2. Now, what's the product of those two things? 0.15 times 0.20. So what do we get? Well, this is 35. Whoops, 0.35, sorry. And 15% of that should be 0.03, so we should get 0.32. Okay, did I get that one right? Boom, yeah, there it is. Okay, now, number 4. This one here has got some monkey work to it. We can do this the long way. What is the probability of students in at least one of 3 classes? So this is a case that we could figure out the sample space, which is not terribly hard, but it is tedious because there's, well, if you figure it out from raw beginnings, there's 3, so there's 6, 18, so you'd have to consider 20 outcomes. However, of those 20 outcomes, 12 of them are going to cancel out. They're going to be in different contexts, but it's the same probability, so they cancel out. So I don't recommend doing that. We're going to answer the opposite question, which is, let's go 1 minus the probability that a student isn't taking any of these classes. It seems like that might be the easier way to do it. So that means we need complements. So probability of not being in biology, put a C on that, is 0.85. And the probability that they're not in chemistry should be 0.80. I'll show you what I mean, I think, about how tedious figuring out the sample space for this is in a minute. Let's just do this computation first. So we want to have the probability that they're not in physics, I'm just going to use the P, and they're not in biology, and they're not in chemistry. This will be 1 minus 0.9, 0.85, and 0.80. I'm just going to do that calculation again, as I was quite distracted this afternoon when I was doing this, and I just want to make sure I didn't screw this up. So 0.9 times 0.85 times 0.8. I got it right. Okay, so this is 612. And the answer then is 0.388. Voila. Now, let's make a bit of room here. I'll show you what I mean about figuring this stuff out and how a lot of the outcomes cancel. So the easy ones are, okay, so they can be in physics, biology, and chemistry. That's one outcome. Now, considering our sample space, we can also have they're not in any of them. These are the easy ones. These ones don't take a lot of rocket scientist talent to figure out. It's the rest of them now. So let's assume there are several cases where we're going to assume in this column that in every case the student is in physics. Now, they can be in physics but not in biology and in chemistry, or they can be in physics and biology but not in chemistry, or we have not, so physics only. So you see how there's just 3 outcomes right there. But now we got to redo this where they're not in that one, they're not in physics or any of these. So we're going to do these are the ones that are going to cancel out, by the way. Most of these we're going to cancel out, I should say. I'm not going to guarantee that they're all going to do. We have 8 left over when we're done. I'm not going to do them all. I just want to show you what you got to do to think your way through this. So here we have, we'll leave that one in, leave this one, now we got that one, and we'll leave that one. So now we have 3 here, plus these 2 up here. There's our 8. Now, let's just take a look at what happens when, I'm just going to do this one. We're going to say that this is the column where biology is always being attended, which means we could have a complement on that. So this means they're not in physics, but they're in biology and chemistry. Now we're going to leave this one, we'll put this one here, and then we have this. So you'll see that this one is already accounted for here. Here we have physics, no to physics, yes to biology and chemistry. Well, that's this outcome here, so this cancels. There's no point in doing it again. And here we have physics and bio, but no chemistry. And that's this one over here, so this cancels. And we have an ad running. So I'm just going to make a note. The rest of the outcomes cancel in a similar manner. Boom. And we're done. Ooh, we got a long ad for this one. Ooh, that one's a minute. What are we selling here? I don't think I've seen this one before. Ooh, that's a horse. So is this one of those, is it her? Or is it Maybelline? Is it Maybelline? I think it's Maybelline. Well, that is, okay, this is kind of interesting. I don't know. Oh, okay, the horse is shown. I've never seen this ad before. It's kind of funky, though. Not just a one-trick pony. A many-trick pony. A multi-talented, small-boned horse. Very good, very good. Okay, I was entertained by that ad. Anyway, now that we're back and live again, the rest of the outcomes in the sample space will cancel out in a similar manner as happened with this column, which is why we end up with these 8. So you can do it that way, as long as there's not too many combinations, or you can go the 1 minus route. Now, in the sense that they repeat, yes, that's what I mean by that. Sorry, that's Cybeam 64, and welcome Cybeam 64. In the context that they cancel, maybe that's not the best word. We can ignore them because let's call it this way. We can ignore them because we've already computed them once. One of the dangers with this stuff is, in the interest or the effort of trying to be complete, oftentimes we end up repeating work, and we don't want to do that. So the rest of the outcomes, maybe I'll reword that. Where's my eraser? Good call on that, by the way. I want to leave this for posterity. So let's do this. The rest of the sample space outcomes are simply duplicates. That we can ignore. Voila. There we go. Not a problem. So I'm going to wrap it up there tonight. That gives us about an hour and 10 minutes of probability, and in my experience, that's probably enough for most people. Oops, get out of there. Get that out of the way. I'm going to do another lecture on probability coming up in a couple of days, because there's quite a number of topics. I still haven't done the Venn diagram decomposition. We'll do that. And the next one, I'll probably do some more examples similar to what we've already done. Thinking about the contingency table ones will make them a little bit harder, maybe. Because I know that midterm's got to be coming up pretty soon. If you started your semester, your spring semester, a couple of weeks ago, there's a midterm in your future here pretty soon. And that's usually timed to follow the probability lectures. And the whole point of that, from my perspective, is to give you a nice body of examples for the midterm. Because at the university, the schools in this city, I know the midterm is usually probability heavy. So, with that in mind, I want to concentrate on that. But I think that's where we're going to leave this tonight. Thanks everyone for joining me, and I do appreciate the interaction on the chat. Zone Ranger, thank you very much. Logarithmic, thank you for joining me. Sensation Black was on here earlier. I have to scroll back to see what happened there. Oh yeah, there he is. And then we had Cybeam 64. So thanks everyone. I appreciate your tuning in for this. And this will obviously be available as a watchable video on Twitch, and I will be uploading this to our YouTube channel as well. YouTube channel is the Tutor Wizard. There's 3 of us. I don't want to. I'm not really big on selling everything, but if you go to YouTube and look up the Tutor Wizard, you will find us. There's Adrian, myself. I'm Tim, by the way, Willow's uncle, and Lorenzo. I know Lorenzo was having some technical trouble with his system. That's why he was absent this week, but I know he's been working through some linear algebra. And like I mentioned earlier, you may find that some of the statistics we're doing can also be done with linear algebra, which is kind of interesting, actually. It's not terribly hard mathematically, but depending on the numbers, might be a challenge to your fraction skills. But that's where calculators come in handy, so I recommend those. Anyway, thank you so much. Give me a couple of days, and I will have Lecture 10 up. And wish you the best of luck with your studies. I'm going to check out now. I think it's time to go and surf the internet, because doom scrolling, it's the thing to do. Have a great night, everybody. Thank you very much.